Hello everyone, my name is Sohaib Bantan and I'm a rising junior at the University of Minnesota studying computer science. This summer I had the privilege of conducting research with the Auton Lab under the supervision of Dr. Chiente and Professor Artur Dubrawski. This summer I did research in deep learning based segmentation for geological core trace and hyperspectral analysis. So that leads us to pop quiz time. The first question is, how much does creating a mine cost? Is it A, hundreds of millions of dollars, B, billions of dollars, C, both A and B depending on scale, or D, yes? Well, the answer for the first question is C. And because of this huge costs, geologists would first need to inspect the area before turning it into a mine. And this process or phase is called exploration drilling, and it mainly concerns collecting core trace as the beginning steps of the process. And so that leads us to the second question. What's true about core trace? Is it A, there are containers that hold cylindrical rock samples from drilling? B, a single borehole that can be 500 meters deep can produce hundreds of these trays? C, geologists label these trays manually? Or D, all of the above? As you might have guessed, the answer is D, all of the above. And so to give a more formal background, let's dive into the crucial early stage of mining, exploration drilling. This process involves extracting potentially kilometers of core samples, and these samples are then placed in trays for analysis. The purpose here is clear. We need to determine if an area is worth a significant investment of developing a mine. As shown in the previous questions, they can be very expensive. And so, given the high stakes, gathering detailed statistics and information is essential. Geologists thus proceed with manual core logging using geological softwares to record core and rubble segments, along with depth markers, all whilst avoiding cracks. However, this process can be time-consuming and may suffer from human inconsistency due to multiple people contributing to the same project. Moving on, once manual logging is complete, we move on to analytical methods like creating mineralogical maps. These maps provide invaluable geological insights, aiding in the decision-making process. Yes, here is where I come in. My aim is to automate this manual process by developing segmentation models that serve as the foundation of the automation. And so, what's been happening around the field? Most research right now is devoted to segmenting cores from the background, with very little dedication towards rubble or crack segmentation. Also, most papers are concerned with object detection via bounding boxes rather than pixel-wise segmentation. And so my motives are to test the effectiveness of instance segmentation models on RGB images of core trays, thus exploring the simultaneous pixel-wise segmentation of the concerned classes. In my case, it's cores, rubble, cracks, and depth markers. I also would like to explore the utilization of the hyperspectral shortwave infrared data and see how it helps in segmenting. And so here is my general workflow for this research project. The data was sourced from our partners at the Colorado School of Mines, so thanks to them. So first, I upload the images into CVAT. I then use that tool in order to create ground truths, which I then train the model and then run the model, the YOLO model, and then the final output would be segmentation masks. So let's get into more detail. The first step is CVAT, the Computer Vision Annotating Tool. And so yes, I first load up the batch of quarter images and I specify the classes before doing anything else. In this research project, I am concerned with chords, rubble, cracks, and depth anchors. I then annotate the classes in the format of polygons because that's what YOLO's instance segmentation require. This is the format that it requires. Similarly, annotations are exported in a format that's not bounding boxes or not rectangles in polygons and exported in COCO format. This is then converted to the YOLO format via the Ultralytics library in the format of polygons. And here's an example of how it would look like. So in the .txt file, it would have multiple lines where each line would represent a polygon, a mask, and it would first include the class number, and then pairs of XY coordinates that represent a point in that specific mask or polygon. Something important that I've realized is when labeling, it is very crucial to maintain consistency. And so I implemented a rubric. And so, for example, if I had a case where there were vertical cracks, I would fall back to my rubric, which was, will this affect depth of registration? And here is a close-up image of the interface of the tool I used. And in regards to the YOLO model, so what is it? It stands for You Only Look Once, and it is a single pass deep learning model that performs real time object detection and segmentation. YOLO version 8 and above support instant segmentation, so more pixel wise segmentation. And for this study, I used the version 11. And Ultratics, the organization behind maintaining these new models, um, offer different variants for the YOLO version 11. And in this study, I used the nano and medium models because they performed best in certain scenarios, and they performed better than the other ones. So the models were trained on the same dataset of 96 annotated images for training and 20 as validation. I also employed early stopping on 10 epochs so that I could prevent overfitting. And so the nano model stopped at 53 epochs, and the medium model stopped at 42 epochs, which are relatively low numbers. So let's do a quick comparison between the two. I found that the nano model was good at Rubble segmentation, and it did not mislabel the background, so the table that the code tray was on, as any other class. However, it did miss occasional core segmentations, so it was lacking a little bit, and it missed the majority of cracks, which was a problem. The medium model, however, was good at segmenting the cracks, um, and it would label nearly all pixels, so it would skip less. However, because of that second point, it would label the background as other classes, so there is some compromisation. And so, because of the pros and cons of the two models, we decided to implement a two-stage approach where we combined the two results. So let's start from the beginning. We first get the RGB image of the core trays, and we feed it into the trained YOLO models, both the nano and the medium. We then get two masked outputs that represent an image array, where each pixel represents a class. So whether it's core, rubble, crack, or depth anchors. And so for each pixel, we implemented this decision tree, where the nano output first serves as the base. We then look at the corresponding media model output and see if it is a crack or not. If yes, we then check if the nano is rubble or not. If it's another yes, we skip over filling the cracks with the medium model, and the final output would be rubble. If the nano was not rubble, however, we would then use the medium model to fill in the cracks. And the reason why this logic was implemented, where we don't fill in cracks over the rubble segmentations, is because rubble might contain similar characteristics and features as cracks, and so we would want to avoid any mislabeling. And so this branches if the medium was crack. What if it was not? What if it was something else? And so then we look at the nano. Was it labeled or not? If it was unlabeled, as shown in the left side image, highlighted in a red circle, we would then fill in whatever the medium model was, whether it was core, crack, rubble, or anything else. If the nano, however, was already labeled and we did not need to fill in anything, it would stay as the base, the nano would stay as the base, and the final output would be the nano output. And so again, we do this for every pixel, and we finally get a pixel map where every single pixel is the output from this decision tree. And so let's compare the performance of these two models, the nano and the medium model, with confusion matrices. We see in the nano model and the medium model that the core segmentation and accuracy was pretty much similar. However, in the nano model, there was a 20% better segmentation of rubble, which is a pretty huge sum. But the cracks would be skipped over by the nano model, which caused an issue. However, as seen in the bottom right box, the unlabeled box, um, the nano model would not segment the background as anything else. But when taking a closer look at the medium model, we see that it had worse rubble segmentation, but it did perform relatively well in the cracks when compared to the nano model. And depth anchors were relatively the same for both. But yes, as we see in the unlabeled box or column, we see that it segments the background as 30% core, 1% rubble, and 1% depth anchor, which is a problem. And so when combining these two models together, what do we get? We get this confusion matrix where in every class we get the best performance of one of the two models. In addition, we can see that in the unlabeled column there are less values. And what does this mean? This means that the model skipped less, and so it would provide more coverage in segmentation, which is also one of the priorities in my task, as segmenting is better, or sorry, misclassifying and mislabeling is better than not labeling at all. And so I provided examples of the segmentations, and this was on a different testing batch that was not the same as the training batch. And I'll let you guys look at the results. And we can see that it would actually cause a partition. For example, in the right image, in the middle core column, we see that it caused a partition between the rubble and the core. Um, and so that's a good thing to achieve as accurate as possible results. Here's another example, and here is the final example. We then plotted the ROC curves, which are the receiver operating characteristics. When taking a close look, we see that there is an anomaly where the model would be, where the plot would be varying and curving, and then hit with a point where it turns linear. And when taking a closer look, we found that it was because of redundant TPR, and the TPR values would only vary when the confidence threshold would reach extremes closer to 1, so 0.85 and above. Um, these ROC curves, they are consistent with what the matrix, what the confusion matrices told us, where the alternating performance is within rubble and cracks for the two different models. And so moving on to the hyperspectral study, we explore the potential of using it for segmentation. So let's talk about hyperspectral data. And so the data is divided into two components, the spatial component and the spectral component. The spatial is in 2D and the spectral is 1D. So this means that in every single pixel, the sensor would measure the spectral bands from 950 nanometers to 2500 nanometers in segments of 10 or steps of 10 nanometers. And so when using these values to calculate reflectance, which is getting the raw measurement and subtracting it from the doc reference, and the doc reference is basically the initial noise at the beginning of the sensor, and dividing all this by the white reference, which is basically how much radiation or reflectance would the sensor have captured fully, and minusing that from the initial noise. And so that would give us the reflectance, and I'm plotting the reflectance versus wavelength. We would see a spectral signature, and these spectral signatures would help us identify what the material is. And so we did a PCA analysis, a principal component analysis on the whole image, so including all of the classes. And we saw that there were three main clusters. The top left one indicated the or represented the tray itself. The top right one represented the background, and the middle one represented the rocks, so the core and the rubble. And so this most likely says that we are able to segment these three things just from the hyperspectral data. But what about segmenting cores from rubble, from cracks, just using the hyperspectral data? And so we did a PCA analysis on the middle cluster, and we saw that it was very clustered and it was very jumbled about. And so performing classification on these three classes was not straightforward and difficult, thus opening the door for a new area of research. And so to conclude my video, fusing the nano and medium models, the version 11 models, led to stronger and more complete segmentation results. And this pipeline that was developed will be adapted to geological softwares used by our partners at the Colorado School of Mines, which is exciting. And also, hyperspectral imaging showed promise for broad class separation. However, further work is needed to fine-grain the material distinctions. And so for future works, we would like to test the segmentation pipeline on new project sites to see how well it generalizes. We would also like to explore ways to use the hyperspectral data more directly to support segmentation. And finally, we would like to extend the pipeline towards turning hyperspectral data into useful outputs like mineral maps, which help guide decisions. I would like to acknowledge the KAUST Gift and Tutor Program for sponsoring this research opportunity, Dr. Chien Tay for his dedicated supervision and mentorship, and Professor Dubrawski for his valuable guidance, as well as Ms. Rachel Berson, Dr. John Dolan, and the RISC team for making this opportunity possible. I also appreciate the support of our partners at the Colorado School of Mines, Dr. Thomas Monike and Zaid Al-Attar. Finally, I sincerely thank all my peers for their collaboration, insight, and support throughout this experience. Thank you so much for listening.